Hi everyone, we're beginning a new chapter today, chapter 16, the kinetic theory of gases. I've listed your reading as sections 16.1 to 16.7, which is the whole chapter. So let's begin. To start with, we'll do a little bit of review of things we've seen before in the course. Then I want to walk through the assumptions we're making for this chapter, and then we'll see the famous Maxwell-Boltzmann velocity and speed distributions. And then I'll show you how we compute different speeds from the distribution, the most probable speed, the average speed, and the root mean square speed for the particles in a gas. You may be surprised to hear that each of these are going to be different numbers. We saw earlier in the course one of the definitions for temperature, and that it was related to the average kinetic energy. This is the source of the statement that I keep making that temperature is kinetic energy. So let's keep that in mind. Next, I'd like to review the difference between velocity and speed. And remember that the difference is if I have a little particle and it's moving in some direction, then that means that in the x direction, it's going to have a certain velocity, and that's going to be different in general than the velocity in the y direction. So remember, velocity has both a direction and a magnitude. However, the speed, which we're going to represent with the symbol v, is just the magnitude of that velocity vector, okay? And the way that we can calculate the speed is it just equals the square root of the velocity in the x direction squared plus the velocity in the y direction squared plus the velocity in the z direction squared, like so. So maybe you can see the Pythagorean theorem at work here. And of course, the kinetic energy, hopefully you remember from physics, the kinetic energy of a particle is 1/2 mv squared, where v is the speed. And if we want to include all the velocities in there, then that's just vx squared plus vy squared plus vz squared. Okay, so at the end of the chapter 11 lecture, I pointed out that that was the end of the thermodynamics portion of the course. And indeed, we are transitioning to something entirely different in this chapter. This chapter is where we barely scratch the surface of statistical mechanics. And there's a lot deeper that we could get into stat mech, but just time doesn't allow. So we'll talk about the few stat mech concepts in this chapter before we move on to kinetics. Okay, so what's the key difference between thermo and stat mech? Thermo considers the macroscopic aspect of systems, but stat mech considers the microscopic, so at the level of detail of the atoms and the molecules. And all of thermodynamics comes from stat mech, and it's really a fascinating, interesting subject, but famously difficult. I think it will be very helpful for you to receive a bit of a perspective on looking at systems from the microscopic perspective. So that's what we're going to do in this chapter. Okay, here are the assumptions that we're going to make for chapter 16. We're going to assume that we're looking at a gas system composed of hard particles that are going to just bounce off each other when they collide. And in fact, quite often we can make the ideal gas assumption that the particles collide very little at all, and we'll make that assumption quite frequently. We'll also assume that they obey Newton's laws, like force equals mass times acceleration. Of course, in reality, the quantum mechanical model is going to more correctly describe what's happening with these particles, but it can be very useful and much easier to deal with Newton's laws and not the Schrödinger equation. Next, I would like to talk about distributions. And so I'm going to draw a distribution right now. Okay, so as you can see, I've drawn a so-called discrete distribution, and this is supposed to represent the probability of finding anyone of a particular age within our class, okay? So if we take a look at what this means that we're quite likely to find people in the class that are between the age of 21 and 22, I would suspect. And we're less likely to find people in the class who are age 20 to 21. And I think we're very unlikely, or maybe there's zero probability of finding anyone between the age of 19 and 20. I could be wrong. Maybe some of you are that age, but I don't think so. And then, of course, there's my age, and I'm way the heck out here. But that's basically what a distribution is. It's a bar graph of probability. Now, there's one other type of distribution that I'm going to draw that I want to introduce to you next if we wanted to consider an even finer, like an infinitesimally fine resolution of ages. Okay, now over here on this graph, if I don't want to split it up by year, but maybe I want to split it up by month or day or second, or just like an infinitesimal small amount of time, then I'm not going to make a discrete distribution. I'm going to make something else. And it's not going to be described by a bar graph, but more like a curve. And it's probably something a little bit like a bell curve like that, where there's a very high probability of someone being 0 years old, like a newborn, and there's very low probability that someone's going to be 100 years old. And this is called a continuous distribution. So as you can see, fewer people make it to 50 years old than are born because maybe they die through accidents or illness or something like that. But do you see the difference between the discrete distribution and the continuous distribution? Hopefully you are able to understand that difference. It's like a bar graph of probabilities where the bars are just infinitesimally close together. On the next slide, we're going to use a continuous distribution to represent the probability of finding particles at particular velocities. So imagine if we have a system of gas particles, and so there's a lot of particles in the gas scattered around randomly, and they all have random velocities. And the length of the arrow represents their relative speeds. As you can see, some of them are going slow, some of them are going fast. And there's a lot more that are going slow than are going fast, because there's a limit to what the speed's going to be given a particular temperature. So we can describe the probability of finding the particle with a given velocity using a continuous distribution like we did on the last slide. And to start with, I'm going to look at the distribution of the velocity in just the x direction for now, and then we'll consider for the other directions too. Okay, so I'm going to draw that distribution now. Remember that velocity can be going in the positive x direction or the negative x direction. So, and those are going to be equal actually. So I'm going to draw the curve, which looks something like this. This curve indicates that the most likely velocity for a particle is going to be 0, but there's definitely non-zero probability that the particles will be moving in any given direction. Notice that this looks like a bell curve. The bell curve has other names. It's also called a normal distribution, and it is also called a Gaussian distribution. And it's amazing how frequently this distribution appears in the world. Like, it can be used to describe grades, it can be used to describe the fluctuation of stock prices. So it appears in a lot of different places, and here is just one of those places. When the bell curve is applied to molecular speed, it's called the Maxwell-Boltzmann velocity distribution. And I'm going to write its mathematical form right now. We use the symbol F to represent the probability of finding a particle at a given velocity, and it's going to equal the mass of the particle divided by 2 pi Boltzmann's constant temperature raised to the 1/2 power, or square root, and then E raised to the negative mvx squared over 2 kBt. So I know this is a complicated function, and it does come from somewhere. I'm not going to walk you through where it comes from, but if you're curious, you can look up where it comes from in the book. For now, it suffices to know that this function describes that curve up there. So we can now use this to figure out information about the velocities of the particles. I'd like to consider a couple more things before we move on to the next topic, and that is, what effect does the temperature and the mass of the particle have on the Maxwell-Boltzmann distribution? Over here, I'm going to plot what low temperature looks like, or what high particle mass looks like. That's going to create a tall, narrow bell curve, something like that. Hopefully that makes sense, because by decreasing the temperature, you're going to be decreasing the average speeds and bringing the velocities closer to zero for each of the particles. Intriguingly, you may also be surprised to see that having a large mass also decreases the average speed that the particles are traveling. If we have a high temperature, or if we have a low particle mass, then the curve gets much broader and would look something like that. Hopefully this also makes sense to you. The higher we raise the temperature, the more likely we're going to find more particles at these higher velocity magnitudes.